Hi everyone, my name is Otomir Jonathan. I'm going to be taking you through cache memory. Yeah, let's dive in. Cache memory is a small high-speed memory component located between the CPU and the main memory, which is the RAM. So it serves as a buffer between the CPU and the main memory, aiming to reduce time required to access data. So when we look at this diagram now, we have the CPU, the cache, and then the main memory. So the CPU gets its data from the main memory, yes. But now, what if it has that data and it's getting it like frequently over and over again, like it stresses it out? So that's where we bring in the cache memory to store that data, so that the next time the CPU needs it, it doesn't have to go to the main memory to get it again. So it checks in the cache and gets it from there. Now this cache memory is divided into three levels: the level 1, level 2, and level 3, where level 1 is the closest to the CPU and level 3 is the farthest. Now what do we mean? So level 1 resides within the CPU, meaning it's faster. And okay, like, yeah, it is faster. Why is it faster? Because we can talk of the bus length to access data. So you'll find that the bus length between the CPU and that level 1 cache memory is very little. So that's compared to the what, level 2 and level 3. So it's the fastest. Level 2 is faster. mm, okay, it's the fastest. Level 2 is faster and level 3 is fast. Yeah, I think that makes sense. Now when the CPU requests data, the cache controller checks if it exists in the cache. Now when it finds it, it gets that data and delivers to the CPU, and that's a cache hit. Now what if when that data isn't there? It's a cache miss. So meaning it misses it and it has to get that data from the main memory instead, which is slower. Now we have this cache read operation where there is a start, then we receive the address RA from the CPU, and then there is this decision it makes, where is the block containing RA in cache memory. Now when we check for that and it's there, we follow this line, we fetch the RA word and deliver to the CPU, and our task is done. Now what if that block isn't there? So we access main memory for the block containing RA, we allocate a cache line for the main memory block, load main memory block into the cache line, we deliver to the CPU, and our task is done. So this is a bit slower, but this is direct when we find it from the cache. Now we also have replacement algorithm in case our cache lines are filled up with blocks. They are filled up and we have nowhere to place the next instructions. So we have the first in first out, where the cache controller, like, it replaces the block which has been there for the longest time. So basically, the block which was loaded first gets removed out first and replaced. So this isn't so effective, because if it was loaded in first, doesn't mean that the CPU doesn't need it. It might be actually the most wanted. So that is where the least recently used comes in. We have the least recently used, the LRIU, where the CPU replaces that block in the set which has been the longest with no reference to it, like it has stayed for a long time without the CPU needing it. So this makes more sense, because if we don't need it frequently, then it can go out. We also have the random. It picks a line at random from the candidate lines, just any line from the cache line. So this one, I don't think it's so effective, because how sure are we that we won't pick out like the most wanted and leave out what we don't need? So those are the replacement algorithms. Now we have the cache mapping functions. We have the direct mapping. So this cache mapping functions are ways that main memory blocks are mapped onto the cache memory, like the cache lines. So direct mapping is the simplest, whereby each block of main memory is mapped into one possible cache line. So our cache memory is divided into cache lines, and we have the tags and we have the blocks. So wait, but we have, where there is direct memory, there is direct mapping, whereby each main memory block is mapped into only one possible cache line. So this is not so nice, because what if we have a reference twice, like in a program, to the same data in the cache memory? There will always be conflicts and cache misses when that comes in. Now associative mapping comes in to overcome the disadvantage of that by permitting each main memory block to be loaded into any line of the cache. So it loads it into any line, like any. So the access is there is reduced cache conflicts, because you can access any of it. Then there's the set associative mapping, which allows the cache lines to be divided into sub caches. So you have the tag, then our blocks are divided into sub caches, and each of those can hold different data. So meaning uh, this is more effective because we can, yeah, I think you see, like we can have a cache block, and then like each of those cache lines are divided into sub blocks storing different data. So this has been it for cache memory. Thank you.